Hello, welcome to Miscellaneous Topics in Simple Harmonic Motion. These are just little extra bits that we're going to cover. Energy of a spring, circles and ellipses, and how to calculate the total spring constant if you've got a couple springs in series or in parallel. So let's get started. So if you remember, the energy of a spring that's been compressed or stretched is equal to 1/2 times the spring constant times the displacement from the equilibrium position squared. So if you think about it, 1/2 kx would equal the average force as you compress it, because it starts at 0 and gets to kx. Remember, force is equal to k times x. So as you compress it, it goes from 0 to kx. So 1/2 kx is your average force. Multiply that by x times distance. You got average force times distance, which is work or change in energy. So anyway, just one way of looking at that guy. Moving along. This kind of stuff comes up a lot in questions. So simple harmonic motion, we're talking about undampened simple harmonic motion. You won't need to know about dampened. For undampened, your energy is just staying constant. You've got potential turning to kinetic and back again. That's the basic idea. So at your equilibrium position, whether it's a pendulum or whether it's a mass spring system, at the equilibrium position, your velocity and kinetic energy are at a maximum. Before it was pulling up, and then it's speeding it up faster and faster and faster, and then right when the force is 0, before it switches to pushing in the opposite direction, your velocity is at a max, therefore your kinetic energy is at a max. Your potential energy is 0 because at the equilibrium position, there's no restoring force. So all your energy is in kinetic at the equilibrium position. And your displacement from the equilibrium position, your acceleration, your potential energy, your force, all that is equal to 0 at the equilibrium position. Force or torque, depending on what you're talking about. At the max displacement, so for a mass spring system, when it stops, it's at one extreme or the other. For a pendulum, when it just slows down, stops, when it's at one max extreme, your displacement or angular displacement, acceleration or angular acceleration, and your potential energy, all of that is at a maximum. Your force as well, or torque, depending on what you're talking about. All that is at a maximum, which should make sense because it is either you've got the most gravity, like your pendulum is at the highest potential energy it's going to have. The thing is stopped, all its kinetic energy is gone. It must have turned into something. It turned into potential. Anyway, so all this junk, all that is at a maximum. Think that through. Make sure it makes sense because it totally can. And right at that point, we're talking about a point like with a pendulum where it slowed down, stopped, or a spring and a mass where it slowed down, stopped. So right there, your velocity is 0, so your kinetic energy has to be 0. All your energy is potential. None of your energy is kinetic when you're at one of these max displacements. And when you're somewhere in between, you've got some in-between mix of potential and kinetic. So that's all I got for that. Let's jump into circles and ellipses. This is kind of like the black sheep of the AP simple harmonic motion family because it is kind of its own thing, but you can use a lot of stuff from previous units. So let's talk about it. One way you can write the equations of motion for a circle, like if you've just got something moving in a circle again and again and again, is you could say, hey, its x position is given by its max radius times cos or sine times some angular velocity times the time, and your y position at any given moment from the center of the circle is equal to its max radius times sine of the angular velocity times time. It doesn't really matter if x is cosine and y is sine, or x is sine and y is cosine. They just have to be opposites. So that is for a circle. We could change it to an ellipse if we just had this as being the maximum x radius, and this is it being the max y radius. So that would be sort of a vertically aligned ellipse. And if these numbers are different, you get an ellipse. If they're the same, you get a circle. It's almost always a circle, but I figured I'd throw an ellipse just in case it comes out. Anyway, so if you want to find total distance away, you could do x squared plus y squared, right? X squared plus y squared is your total distance from your center point squared. And if you notice you do that, you'll end up with, this is all a proof stuff, so not super important, but let's take a quick look. So x squared plus y squared, here's our formula for x squared, here's our formula for y squared. We can collect like terms. One thing you should know, it's a trig identity, is cos squared plus sine squared is equal to 1. So in this case, all this is equal to 1. And so at all points in time, so regardless of time, your distance from the center point is your radius, or your squared distance from your center point is your radius, yeah. Anyway, so this just proves that, hey, this will be your radius of your circle. And so the next thing we'll talk about, what's the velocity at a given point. Now there's a couple ways you could do it. I'm going to go through the long way and then I'll just tell you the short way. Just very quickly. So your velocity, like your Vx and your Vy, is just your derivative of your x velocity at a given point is the derivative of your x formula. So I just took the derivative of that. Your y velocity at a given point is the derivative of your y position. So we'll end up with this. Notice anyway, prove to yourselves that this is the derivative of the formula we had for x up there, and this is the derivative of the formula we had for y. And then notice we can collect like terms again. And what's sine squared plus cos squared again? Sine squared plus cos squared, as long as it's the same thing inside, is always equal to 1. So we find out that no matter what, your total velocity is always going to be your angular velocity times r, which should be familiar. So here's the shortcut. So we go through all this, we could take our derivatives and we could find the total velocity by doing like Vx squared plus Vy squared, doing sort of a Pythagoras with it and doing our sine squared plus cos squared equals 1 identity. Or we could remember a circular motion unit where our velocity is always equal to the angular velocity times r. Yeah, that's one of our radian things. Remember, d equals theta r, v equals omega r, and the next one, a equals fish r. So we'll do that here. So really, you should probably just remember the formula from circular motion. Anyway, with exactly the same logic, we can take the derivative again. Derivative of our x velocity is our x acceleration. Derivative of our y velocity is our y acceleration. We can collect like terms. We get another cos squared plus sine squared. Cos squared plus sine squared equals 1. Once we've solved for our total acceleration, we find at all points our acceleration is equal to omega squared r. So just like we had before. If you remember that one, that was one of the, we used it a lot for net force, centripetal force. Like, hey, your centripetal force is equal to mv squared over r, or m4 pi squared r over t squared. But one of the new ones we had this year is your centripetal force is m omega squared r, m angular velocity squared r. So yeah, you can still use that guy. Now our last topic, which I'm going to try and get through quick because I've been going on, is adding spring constants. So if you were adding spring constants in parallel, Okay, let's talk adding spring constants. So if you got a couple springs in parallel like this, it's super easy to come up with the total spring constant. It's just, you just add up the individual spring constants. So if you've got this guy right here with a spring constant of K1, this guy here with a spring constant of K2, this guy here with a spring constant of K3, your total spring constant is just them added up, just like resistors in series. If you have them in parallel, it's a little bit more complicated, but fortunately the formula is still familiar. So if you have all of these in common, your total, or 1 over your total spring constant is equal to 1 over your first spring constant plus 1 over your second spring constant plus 1 over your third spring constant. So springs in series add like resistors in parallel. That's the only trick. Remember your circuits and basically just do the opposite. Parallel springs, like a series circuit, just straight adding them up. And springs in series, add like resistors in parallel. That's it. Thanks for watching. Like and subscribe.